Lesson 1.1, Investigating Special Products. Okay, let's talk about our learning goals really quickly. What are we going to be doing in this lesson? Well, the first goal of this lesson is to expand special binomials. So what are special binomials? Okay, they are in, these three forms. Okay, and we are going to find a pattern in the result. So that's our first goal for today. Our second goal for today is use these patterns to recognize when special binomials have been expanded. Okay, so basically this lesson is all about patterns and recognizing them. So let's start with the first one. It's an investigation. So what we want to do is complete the following table. And the way we're going to do this is by taking the binomials that were given and we are going to expand them. As you know, when we expand, we use the distributive property. So our expanded trinomial is going to look like this. So x times x is x squared, okay, plus 3x plus 3x plus 9. And then what we can see is that actually the two terms in the middle add together. So I know that my final answer is x plus 3 squared is x squared plus 6x plus 9. Let's try another one. So be really careful. There's a common mistake here. Some guys think like this is just x squared plus 9, but it isn't. Okay, you have to actually write the terms out twice and multiply them. Okay, so 2x times 2x is 4x squared. 2x times 3 is 6x. 3 times 2x is 6x. And 3 times 3 is 9. Hopefully, you're starting to see a pattern. And that pattern is that the middle two terms, these two, they're always the same and they always add together. They're always like terms. So let's have a look at the pattern that we're seeing here. Question number 2 says, compare the first term in each trinomial. Trinomial means 3 terms, right? First term in each trinomial to first term in each binomial. Okay, so here's the binomial. Okay, and then this is the resulting trinomial, right? All right, so let's compare the first term in each trinomial to the first term in each binomial. So what do I notice? What is the pattern here? Well, what I should be seeing is actually that the term in the trinomial is the term in the binomial raised to the power of 2. 2x squared is 4x squared. 2x all raised to the power of 2 is 4x squared. So what I can see is the first term in the trinomial is equal to the first term in the binomial raised to the power of 2. Now let's have a look at the second question. It says compare the last term in each trinomial to the second term in each binomial. Okay, so here's the last term in the trinomial, and here's the second term in the binomial. And we can see a pattern here as well. Okay, we can see that the last term in each trinomial is equal to the last term in the binomial raised to the power of 2. So that works for the last one as well. We have 3y raised to the power of 2. 3y to the power of 2 is equal to 9y squared. All right, and last but not least, let's compare the middle term to the trinomial. Okay, this one's interesting. So it says compare the middle term in each trinomial to both terms in each binomial. So what does that mean? How does 6x, okay, relate to x plus 3? How does 12x relate to 2x plus 3? And how does 30xy relate to 5x plus 3y? Well, if you look at it hard enough, what you'll notice is that all of the middle terms are multiplications of each of the two terms in each binomial, also multiplied by 2. So, for example, this middle term is x times 3 times 2, which is 6x. This middle term is 2x times 3, which is this term and this term, multiplied by 2. Okay, and also this term, 30xy, is equal to 5x times 3y times 2. That's 30xy. So we can say that the middle term is equal to first term times second term times 2. So if I were to take a new binomial, a plus b squared, okay, and I were to try to expand that using the pattern, well, I would know that my first term in the trinomial is a squared, my last term in the trinomial is b squared, and my middle term is going to be 2 times a times b. So instead of using the distributive property every single time, I can use this pattern as a bit of a shortcut. So let's try one together. Let's just use the general rule and the pattern without actually using the distributive property. So this looks a lot like a plus b squared, and I know the pattern is a squared plus 2ab plus b squared. And I know that x is going to be my a term, and b, 12, is a lot like b. So I know if I expand it, this is going to be x squared plus 2 times x times 12 plus 12 squared. I could have done this all in my head probably, but I just wanted to show you an extra step. So I can use a general rule to expand instead of writing the bracket out twice. So for example, here, I know this is 3x squared plus 2 times 3x times 2 plus 2 squared. So we've got 9x squared plus 2 times 3x is 6, times 2 is 12x, plus 4. So I can use this pattern instead of the distributive property. Investigation 2 is very, very similar, so I'm just going to do it quickly. I'm going to ask you to copy this down. All right, so let's have a look at the pattern, and we'll notice that it's very similar. So if I compare the first term in the binomial with the first term in the trinomial in all three of these, I can again see that the first term in the trinomial is equal to the first term in the binomial squared. And we're going to see the same thing here. The last term in the trinomial is the last term in the binomial squared. So I can use my highlighter again. Right? So I can see that negative 4 to the power of 2 is 16. Negative 5, right? We know that negative 4 squared equals 16. Negative 5 squared is 25. And negative 7y squared is 49y squared. So that works out. All right. And what we'll notice as well is if I look at the middle term, again, it's a little bit trickier to see what this pattern is. Okay. But if I compare this to the two terms in my original binomial, I can see that my middle term is again, okay, equal to the first term of the binomial times the second term in the binomial, okay, times 2. In this case, these ones are negative though. So for that first example here, okay, I know that my first term is x and my second term is negative 4. So x times negative 4 times 2 equals negative 8x, which is what I have here for my middle term. Okay, so let's generalize this pattern. Again, we don't have to write it out twice, okay, and use the distributive property because we know the pattern instead. If I have a minus b squared, I know that when I expand it, I'm going to get a squared minus 2 times a times b plus b squared. And be careful, we know this is a plus because all of these here, okay, even though they're negative, when we raise it to the power of 2, that negative goes away. Okay, so our last term in the trinomial will still be positive. So let's try this one using the pattern or the general rule. So we have to be careful with substitute or negative values here, because if I look really carefully at this, I know that my a value is x and my b value is not negative 9, it's actually 9 because the negative values match up here. So I'm not going to include negative in my b value. My b value is in fact just 9. So if I want to use the pattern here, I know it's a squared minus 2ab plus b squared. So I'm going to get x squared minus 2x9 plus 9 squared. So that's x squared minus 18x plus 81. Now you might be wondering why I'm not using the distributive property, but the whole point of this lesson is to recognize the pattern and use it instead of using the distributive property. So we're going to see why that's important in a second. So if I expand this, I can see that my a term is 3z cubed and my y term is, my b term is 4y. So I have 3z cubed and 4y plus 4y all squared. So what do we have here? That's 9z to the power of 6 minus 24z cubed y plus 16y squared. All right, one more table, but this one looks a bit different. Okay, this one looks a bit different because there is no power of 2. So for this one, what we're doing is using distribution. So here I've got x squared minus 4x plus 4x minus 16. And what's really special here is we'll notice that the terms in the middle actually end up canceling out. So in the end, x plus 4 times x minus 4 is equal to x squared minus 16. There is no middle term. All right, so now let's look at the pattern here. How are the two binomials in the first column alike and different? So what we're asking here is when I look at the binomials x plus 4 and x minus 4, I can see actually that the binomials are the same and that the terms are the same. Okay, but the signs in between them are different. Okay, so we can see that one is an x plus 4 and the other is an x minus 4. So there's a clear pattern here. Okay, we can just see that the signs are actually different, but the terms are the same. How do the terms in the product compare with the two binomials in each multiplication? Well, I think what we can see pretty clearly, even if we just look at this first one here, is that the result is always first term squared minus second term squared. And explain why there are only two terms in the simplified product. And I think we can say that because the two middle terms cancel out. And that's because of the signs. They are different. So if I asked you for a general rule for expanding things of this type, okay, we would know that the answer is always going to be the first term squared subtract the second term squared. So if I compare y plus 7, y minus 7 to a plus b, a minus b, I know that pattern is going to be a squared minus b squared. So in this case, it's going to be y squared minus 7 squared. We'll notice that it doesn't matter if the plus goes first and the minus goes second, or vice versa. Okay, it will always work out that the middle terms will cancel out and there will be a subtraction between these two terms. All right, so I'm going to give you some time for independent practice and you can check your answers back here. So the idea here is to use special products where possible, and that's just to save you time, but I would highly recommend doing it rather than using distribution so that you can get familiar with the pattern. So for example, we can see that this is a pattern, and I know that my answer is going to be 4x squared minus 9. So rather than use expanding for all of this, that's what I'm going to do. I also know that this is a pattern. Okay, this is a minus b squared, and I know the pattern there is a squared minus 2ab plus b squared. So I can just write that down. I know it's going to be 9x squared minus 2 times 3x times 2 plus 4. 4x squared minus 9. Okay, so there you have that. Now I'm going to try to use the pattern backwards. So I hope you guys are all familiar with the show Jeopardy! Basically, you get the answer in Jeopardy and you're trying to figure out what the question was. So I want you to think about that this way with polynomials. So what we've found out is that we have patterns when we expand. So I should be able to look at the answers and figure out what the questions were, if these were indeed special products. And I will tell you that I'm not trying to trick you here. All of these have one of these three patterns. So let's start with the first one. Well, something that's really obvious about these patterns are the number of terms and also the signs. So I can see here that I have three terms that are separated by addition. So I know that the only possibility here is a plus b squared. Next, what I'm going to do is I'm going to look at the first term and the last term here. And I can notice that they're both perfect squares. So my hunch is that it's x plus 3 squared, right? Because the square root of x squared is x and the square root of 9 is 3. But I have to make sure that it matches up with the middle term. So if I take 2 times x times 3, or if I expand this, which I can check, I can see that my middle term should be 6x, which it is. So that's how I can sort of work backwards from the trinomial I'm given and say that the question was x plus 3 squared. Okay, same deal with the second one. So if I look at this, it's pretty obvious. I have three terms and one of them is separated by a minus sign and one of them is separated by a plus sign. So I'm going to take a guess, and I'm going to guess that this is actually x minus 2 squared, because the square root of x squared is x and the square root of 4 is 2. And I can check this if I want. So if I expand this, I get x squared minus 2x plus 4, which is indeed the question I got. So I know that actually this is the same. If this was Jeopardy, okay, if the expansion is x squared minus 4x plus 4, I know that the question was x minus 2 squared. All right, so the last one here, this one really sticks out because it only has two terms. And what I can see is that they're also both perfect squares, right? X squared is x squared and 9 is 3 squared. So actually, I'm going to take a guess that this is x plus 3, x minus 3. And if I try to expand it, I get x squared plus 3 minus 3x. Okay, minus 3x plus 3x minus 9, which indeed, because those two cancel out, is x squared minus 9. So I know that my Jeopardy question was x plus 3, x minus 3. So I want you guys to try the next ones, okay? And I will give you the answers in this video.